everyone. I welcome you all to this digital classroom for the subject control systems. In the previous lecture, we discussed about the concepts of stability. And today, we are going to discuss about the necessary condition for stability and the Routh stability criterion. During the previous lecture, we justified that if all the poles are on the left half of the S-plane, then the system is stable, and if all the poles lies on the right half of the S-plane, then the system is unstable, and if all poles are on the imaginary axis, then the system is said to be marginally stable. We have justified the statement by taking the characteristic equation of a closed loop system, and then we plotted the location of the pole on the S-plane and we analyzed its corresponding response. We know that G of S can be represented in three forms. G of S can be represented in pole zero format, which is given by S plus A into S plus B and so on, divided by S plus C into S plus D. And this format we call it as pole zero format. As well as G of S can be represented in terms of time constants. Also, G of S can be represented in terms of a polynomial, which is given by G of S equal to N of S divided by D of S is equal to Bm s to the power m plus Bm minus 1 s to the power m minus 1 plus and so on towards B1 S1 plus B0, the whole divided by An s to the power n plus An minus 1 s to the power n minus 1 and so on towards A1s plus A0. With respect to module 2, we have represented G of S in terms of pole zero format, whereas in this case, we are representing G of S in the form of a polynomial. The poles of the system G of S are the roots of the denominator polynomial D of S, that is the value of S for which D of S is equal to 0. And the zeros of the system G of S are the roots of the numerator polynomial N of S, that is a value of S for which N of S is equal to 0. Now, our point of interest is the characteristic equation 1 plus G of S into H of S is equal to 0. And we have to calculate the roots of this characteristic equation, that is nothing but the poles, and we are going to analyze the location of the poles and we will be judging about the stability based upon the location of the poles. If it is on the left half of the S-plane, we can say that the system is stable, and if the poles are located on the right half of the S-plane, then we can say that the system becomes unstable, and if the poles are located on the imaginary axis, we can say that the system is marginally stable. But for a higher order system, it is very difficult to find the roots. Hence, we can make use of Routh Array's criterion. So let us look into the necessary condition for stability. We know that the test for stability is with the question that whether any roots are present in the right half of the S-plane. If so, we can say that the system is unstable. To ensure the roots of the characteristic equation to lie in the left half of the S-plane, it is necessary that all the coefficients of the polynomial should be negative and all the coefficients of the characteristic equation should have the same sign. And also, there should not be any missing coefficient, that is, all power of S must be present in descending order from n to 0. Let us take an example. Consider a system with a characteristic equation given by S cube plus S square plus 2S plus 8 is equal to 0. And if I calculate the roots of this equation, we get S is equal to minus 2 and 0.5 plus J 1.936 as well as 0.5 minus J 1.936. In this case, it is very clear that 0.5 plus and minus J 1.936 lies in the right half of the S-plane. The roots are complex conjugate and it lies in the right half of the S-plane. But the given condition is all the characteristic equation. If you look into all the coefficients of the characteristic equation, they are non-negative as specified before as a necessary condition. In this example, the system has become unstable as we have two poles on the right half of the S-plane. So it is clear that the system is unstable as we have two roots on the right half of the S-plane. But in the previous slide, we have stated that the necessary condition is that all the coefficients are non-negative. Even though all the coefficients are non-negative, in this case, the system has become unstable and it is not guaranteed with stability. Let me repeat you once again. In this case, if you inspect all the coefficients are non-negative, which meets the necessary condition. But if you look into the roots of this equation, we have two roots in the right half of the S-plane, which is making the system to be as unstable. Hence, we can introduce another statement that these are not a sufficient condition to ensure stability. This can be a necessary condition, but not a sufficient condition to ensure stability. Now let us look into the steps involved in Routh-Hurwitz criterion. This method yields stability information without the need to solve for the closed-loop system poles. As we know that for a higher order system, it is very difficult to find out the roots. This RH criterion gives you the solution for it. Using this method, we can tell how many closed-loop system poles are in the left half plane and in the right half plane as well as on the j omega axis, that is the imaginary axis. Notice that we say how many but not where. It just gives you the count of how many poles lies in the left half of the S-plane and how many poles which lies in the right half of the S-plane and how many poles which is on the imaginary axis. This method requires two steps. The first step is to generate a table called as Routh table or Routh array. The second step is to interpret the Routh array or the Routh table to tell how many closed loop system poles are in the left half plane and the right half plane and on the j omega axis. Let us generate the Routh array first. Write the polynomial in S in the following form. The polynomial DFS is represented as a0 s to the power n plus a1 s to the power n minus 1 plus a n minus 1 s plus an equals to 0. The denominator polynomial is represented as d of s is equal to a0 s to the power n plus a1 s to the power n minus 1 and so on extended up to a n minus 1 s plus an, finally the constant, which is equal to 0. Now let me write the s terms first, starting from s to the power n, s to the power n minus 1, s to the power n minus 2, s to the power n minus 3, and so on up to the constant value s to the power 0. S to the power 0 is nothing but 1, and it is nothing but the last term in this denominator polynomial. Now we can arrange the coefficients of the characteristic equation in the first two rows as follows. The coefficient of s to the power n is a0 and can be written here against the first row as a first element. And immediately we have the coefficient s to the power n minus 1 as a1, which has to be written immediately below the first element as a1. And similarly, we can fill up the rest of the coefficients in the first two rows as a2. Then immediately below a2, we can write the coefficients of s to the power n minus 3 as a3, followed by a4, a5, and a6, a7, and so on. And we can fill up the first two rows making use of the given polynomial following this procedure. The next step is to fill up the remaining rows by using the following procedure. We have filled up with the first two rows. Now our point of interest is with respect to the third row and to find the element B1. As said before, only the first two rows of the array are obtained from the characteristic equation and the remaining are to be calculated as follows. So to calculate B1, B1 is given by A1, A2 minus A0, A3 divided by A1. So to fill up the third row, we have to make use of the previous two rows and we have to trace it. We have to use the formula A1, A2 minus A0, A3 divided by A1. It has started from A1 and it has been ended at A1. Similarly, to fill up the second element of the third row, to obtain B2, we can make use of the previous two rows and the formula is given by B2 is equal to A1, A4 minus A0, A5 divided by A1. And now we have obtained for the element B2, that is for the third row second element. Similarly for B3, we can follow the same procedure and B3 is given by A1, A6 minus A0, A7 divided by A1. We can fill up the complete row making use of the previous two rows as a reference, and the most important thing to be noted down here is for the complete row we have taken A0, A1 as a reference and we have shifted each column for each of the element and we have obtained the value for B1, B2, B3, B4 and so on, and the complete row can be filled. So let us try to fill the next row s to the power n minus 3 following the same procedure. To calculate for C1, C2, C3, C4 and so on, the same pattern of cross multiplying the coefficients of the two previous row is followed and C1, C2, C3, C4 etc. can be evaluated. That is exactly the fourth row. So to fill up the fourth row, we have to make use of the previous two rows as a reference and we have to follow the same pattern of cross multiplication. Now let us find for C1. C1 is given by B1 A3 minus A1 B2 divided by B1. Similarly, to compute for C2 is given by B1 A5 minus A1 B3 divided by B1. Similarly, we can compute for C3, C4 and so on, and a complete row can be filled. This process is continued until the nth row has been completed. We have to follow this procedure until the complete nth row has been completed, following the same pattern, making use of the same formula. And now let us move on to the next step, that is to interpret the RH table. Once after computing the RH array, here we have to look into the first column of the RH array, which has been highlighted here. We have to look into the sign changes of the elements, that is the coefficients of S with respect to the first column of the RH array. From A0 to A1, we have to check for whether there is any sign change. And then followed by A1 to B1, we have to check for whether there is any sign change. Then from B1 to C1, and we can keep on inspecting and checking out for whether there is any sign change throughout the first column of the RH. And if there is no sign change, then you can say the system is stable. And if there is a sign change, then the system becomes unstable. And the number of sign change will be equal to number of roots in RHS. So let us assume that the first coefficient is having a sign plus, the second with plus, and the third is minus, then the fourth is plus, and finally all are plus. It is just an example. So now This is just an example. Hence now, if you look into the first column of the RH table and if you look into the sign, moving from the first element to the second element, both are having the same sign, so there is no sign change. We should keep on asking the question whether there is any sign change. No, there is no sign change. And if you move on from plus A plus, and if you move on from plus AN to minus B1, is there any sign change? Yes, of course, there is one sign change which has changed from plus to minus. So we can make a note as one sign change. Then when we move on from B1 to C1, there is a sign change again from minus to plus. So again, we could able to see a sign change. So if you have a total of 2 sign changes as of now, then if you proceed further, all are plus, that is the same sign. So there is no sign change here. Put up a question again and again, whether there is any sign change, whether there is any sign change, and make a count of it and write the number parallelly. So in this case, as there is a sign change, the system is unstable. Hence, in this case, as there is a sign change, the system becomes unstable. Also, the number of sign changes will be equal to the number of roots in the left half plane of the S-plane. Hence, here in this example, there are 2 sign changes. Hence, it is very clear that the number of roots present in the right half of the S-plane is 2. So making use of this RH criterion, following the 2 steps, the first step is to generate the RH table. Once after generating the RH table, we have to interpret the RH table and we can make use of the first column of the RH table and inspect whether there is any sign changes in the first column of the RH table. And finally, if there is any sign change, we can say that the system is unstable, and in addition to that, the number of sign changes will give you the number of roots which is present in the right half of the S-plane. So, the Routh stability criterion states that the system is stable if and only if all the coefficients of DFS are positive and all the terms in the first column of the array have positive sign. And this is not a sufficient condition. It can be a necessary condition, but it is not a sufficient condition. So, the number of changes in sign of the coefficients of the first column of the array is equal to the number of roots of the DFS with positive real part. That is, roots lie on the right half of the S-plane. As discussed already, the number of sign changes gives you the number of roots which is present in the positive real part, which is nothing but the poles which is present in the right half plane of the S-plane. Let us solve few problems related to Routh stability criterion. Let me take this example. Consider the following polynomial: s power 5 plus 4s power 4 plus 5s cube plus 3s square plus 4s plus 2 equal to 0. Determine the number of unstable roots. The first step is to generate the Routh array or Routh table. Hence, let me write the S terms. Starting from the highest power, s power 5, s power 4, s power 3, s power 2, s power 1 and s to the power 0. And let us write the coefficients of s and fill the first 2 rows. The coefficient of s to the power 5 is 1. 1 is written here. Immediately below that, we have to write the coefficient of s to the power 4. It's 4 here. And the coefficient of s cube is 5. It has been written here. And the coefficient of s square is 3. It has been written here. And s is 4. It has been written here. And a constant 2. So we know the procedure to fill up the first 2 rows. Once after filling up the first 2 rows, we know the procedure to fill up the third row, making use of the formula. Four into 5 minus 1 into 3 divided by 4. Hence, the third row first element will be 4 5s are 20 minus 3 divided by 4. Hence, we can obtain 4.25 as the first element. Similarly, we can fill up the third row second element making use of the pattern 4 into 4 minus 1 into 2 divided by 4. Hence, we can obtain 4 fours are 16 minus 2 divided by 4, which is equal to 3.5. I have filled up in the third row second element. Similarly, third row third element will be equal to 0. If we trace the pattern, 4 into 0 minus 1 into 0 divided by 4, we get 0. Hence, we have done with the third row. To fill up the fourth row, we have to take the previous two rows as the reference and we have to follow the same pattern. So the fourth row first element can be filled by the formula 4.25 into 3 minus 4 into 3.5 divided by 4.25. Hence, I get minus 0.2. Similarly, for fourth row second element, I can make use of the formula 4.25 into 2 minus 4 into 0 divided by 4.25. Hence, I get 2 here. Then for fourth row third element, it will be equal to 0. Now to fill up the fifth row, I have to take the previous two as the reference and follow the same procedure. Hence, I get 39, 0, 0. And to fill up the sixth row, I have to make use of the previous two rows as a reference. Hence, for fifth row first element, 39 into 2 minus of minus 0.2 into 0 divided by 39. Hence, it is 2. And the rest of the terms will be equal to 0. Once after completing with the Routh array, the next step is to interpret with the first column of the Routh array which we have obtained. Now we have to represent the sign of the elements in the first column. Hence, it's plus 1, plus 4, plus 4.25, minus 0.2, plus 39, and plus 2. Now we have to look forward and inspect whether there is any sign changes in the first column of the Routh array which we have generated right now. So starting from the first element towards the second element of the first column, we have to ask the question, is there any sign change? No, of course, there is no sign change. Then we have to proceed from second to third. Again, no sign change. When we move from third to fourth, there is a sign change from plus to minus. So I could able to identify one sign change. Then for the next step, there is again a sign change from minus to plus. Then I can number it as 2. It is very clear that I have encountered 2 sign changes so far. Moving on to the next stage, it's plus to plus, hence there is no sign changes. So overall, there is a sign change of 2. Hence, we know that if there is a sign change, then the system becomes unstable. Yes, we have a sign change and the system has become unstable. And apart from that, the number of sign changes gives you the number of roots in the right half plane. As we have 2 sign changes in this example, we have 2 roots in the right half of the S-plane. Hence, we can conclude that there are 2 sign changes. Hence, the system has 2 poles in the right half plane. Hence, the system is unstable. The question is to find the number of unstable roots. So, it has been clearly written in the answer that 2 poles in the right half plane, which makes the system as unstable. Let us solve few more example problems. Examine stability of f of s is equal to s cube plus 6x square plus 11s plus 6 is equal to 0. As stated previously, the first step is to generate the Routh array. So we have the coefficients of S cube as 1 and the coefficient of S square is 6, coefficient of S is 11 and finally the constant is 6. That as the highest power of S is 3, we have n is equal to 3, which means that we get 3 roots in this example. The first step is to write the S terms starting from S cube, S square, S to the power 1 and S to the power 0. Then we know the procedure to fill up the first two rows. Let us fill up the first two rows. 1, 6, 11, 6. The rest of the terms will be 0, 0. To fill up the third row, we know the procedure that we have to make use of the previous two rows as a reference and we have to follow the pattern 6 into 11 minus 1 into 6 divided by 6. Hence I get 10. Similarly, for the third row second element, we have to follow the pattern 6 into 0 minus 1 into 0 divided by 6. Hence it will be equal to 0. To fill up the fourth row, we have to make use of the previous two rows as a reference and follow the same formula. Fourth row, first element can be given by 10 into 6 minus 6 into 0 divided by 10. Hence I get 6. And fourth row second element will be equal to 0. Once after generating the Routh array, the next step is to interpret with the Routh table and we have to look into the sign of the elements in the first column of the Routh array. So if you look into the first element of the Routh array, the first element of the first column is positive and the second element is positive and the third one is positive and the fourth one is also positive. So it is very clear that there is no sign changes when we proceed throughout the first column. Hence you can say that there is no sign change, hence the system is stable. In this example, it is very clear that the system is stable as we don't have any sign changes. Hence we can say that as there is no sign change in the first column, the system is stable. Let us try with another example problem. Comment on the stability of a system using Routh stability criteria whose characteristic equation is given by s to the power 4 plus 2s cube plus 4s square plus 6s plus 8 is equal to 0. How many poles of the system lies in the right half of S plane? So the first step is to generate the Routh array. Let me arrange the coefficient first starting from s power 4, s cube, s square, s to the power 1 and s naught. And let us fill up the first two rows. The coefficient of s power 4 is 1 and s cube is 2. Then s square is 4 and s is 6. And then we have a constant 8 and we can make the rest of the term to be a 0. To fill up the third row, we have to make use of the previous two rows as a reference and we have to follow the pattern 2 into 4 minus 1 into 6 divided by 2. Hence we get 1. Similarly, to fill up the third row second element, the formula which we use is 2 into 8 minus 1 into 0 divided by 2. So we get 8. The third element will be 0. To fill up the fourth row, we have to take the previous two rows as a reference. Fourth row first element can be given by 1 into 6 minus 2 into 8 divided by 1. Hence we get minus 10. And the second element will be 0. To fill up the fifth row, we have to make use of the previous two rows as a reference, and we have to make use of the formula minus 10 into 8 minus 1 into 0 divided by minus 10. Hence, I get plus 8. And the next element will be equal to 0. Once after generating the Routh array, we know the procedure. We have to interpret with the Routh array, looking into the signs of the first column of the Routh array. So if you look at the first column, we can represent the sign for the first element as plus, second element is plus, and the third element is plus, and the fourth element is negative here minus, and the fifth element is plus. Now we have to keep on inspecting whether there is any sign change when we move from the first element towards the last with respect to the first column of the Routh array. So from plus to plus, no sign change. Then again from plus to plus, no sign change. Then we have a sign change when it is moving from plus to minus. So I have one sign change here when it is moving from third element to the fourth element. Then again moving from fourth element to the fifth element, again I have a sign change from minus to plus. So as a total, I have two sign changes in this example. Hence, do we have any sign changes? This is what I told you from the beginning. You should keep on asking this question. Sign changes? Yes, I have a sign change. And how many? There are two sign changes. As there is a sign change, the system becomes unstable and the number of sign changes will be equal to number of roots in the right half plane. Hence, as the count is 2 here, we have two roots in the right half of the S-plane, which has been asked in the question that how many poles of the system lies in the right half of the S-plane. Hence, we can write the statement as there are two sign changes in the first column. Hence, the system is unstable with two poles in the right half of the S-plane. Let us try out with one more example problem. A unity feedback control system has G of S is equal to 2k divided by S of S plus 1 into S plus 5 plus 20, where R of t equal to 2t. It is desired that for a ramp input ESS less than or equal to 1.5. What minimum value must k have for this condition to be satisfied? With this k, is the system stable? So this problem is a combination of steady state error concepts added up with stability analysis. So the first half is related to module 2, in which we have done so many problems related to the steady state analysis, calculating the position error constant, velocity error constant, and the acceleration error constant, and then we used to calculate the steady state. So let us recall those concepts once again and try to find whether the system is stable or not. Let me solve this problem. Let us write the given data first. For a ramp input R of t. So given is a ramp input and it has been given with an amplitude of A is equal to 2 in the question. Hence, as it is a ramp input, we have to calculate the velocity error constant Kv, which is given by limit s tends to 0, s into g of s into h of s. As it is unity feedback, h of s will be equal to 1 and g of s is given in the question. So let us substitute for limit s tends to 0 s into g of s. As s tends to 0, we get 20k divided by, in the denominator we have 5 plus 20, so we get 25. So kv will be equal to 20 divided by 25 into k. Now, given ESS is equal to 1.5 in the question, hence we can write the formula for ESS as A divided by kV, which is equal to 1.5. And we know kV is 20 divided by 25 into k. From this equality, I can simplify further and find out the value of k, which is 1.667, and I can take it as a minimum value as ESS less than or equal to 1.5. Hence, I have found the value for k, that is minimum value for k, which is satisfying the condition for the steady state error is less than or equal to 1.5. Once after finding the value of k, the procedure is now very simple. Our point of interest is to find the characteristic equation 1 plus g of s into h of s equal to 0. Hence, in the given data g of s, we have to substitute for k is equal to 1.667 and then simplify in the characteristic equation, and we have to simplify further and we have to represent it in the form of a polynomial, which is given by s cube plus 6s square plus 25s plus 33.33 equal to 0. Now we have reached the step which we have followed for few of the example problem in which the given data was a polynomial. Then we used to represent this polynomial in terms of Routh array, and we generated the Routh array. Then we interpreted looking into the first column of the Routh array whether there is any sign change, and if there is a sign change, we estimated that the system is unstable, and if there is no sign change, then we told that the system is stable. Now we have reached this point exactly in which the procedure now it is very simple. We have to write the S terms first. That is, we are going to generate the Routh array right now. I have written s cube, s square, s to the power 1 and s naught. And we know to fill up the first two rows, taking the coefficients of s cube starting from s cube 1, 6, 25, 33.33, 0, 0. To fill up the third row, we have to make use of the previous two rows as a reference, and the third row first element can be written as 6 into 25 minus 1 into 33 divided by 6. Hence I get 19.44, and the third row second element will be equal to 0. Similarly, to find the elements in fourth row, I have to make use of the previous two rows as a reference, and fourth row first element can be given by the formula 19.4 into 33.33 minus 6 into 0 divided by 19.44. 19.44 in the numerator and in the denominator will get cancelled out. Hence I get 33.33. And the fourth row second element will be equal to 0. Hence, now we are left out with the interpreting with the Routh array. We have to look into the first column, and we could able to notice that all the signs are positive. Hence, there is no sign change. Hence, the system is stable. As there is no sign change in the first column, the system is stable for k is equal to 1.667. Hence, we have done with many example problems today, and in the next lecture, let us solve few more example problems related to the Routh stability criterion with few special cases. Thank you.